In this video, we'll continue our discussion of the estimation of causal effects. Recall from last lecture that we considered the causal linear model y equals beta 0 plus beta 1x plus u, where x is the causal variable of interest, beta 1 is the causal effect of x on y, and u summarizes all the other factors contributing to the generation of y. In general, in a causal regression, in a causal model, the variable x and the variable u may be correlated. So the correlation between x and u is not necessarily zero, which means that the orthogonality condition may or may not be satisfied in a causal model. So what that means is, in general, running an OLS regression, OLS estimator for beta 1 from the regression of y on x may or may not consistently estimate beta 1. However, we did discuss one setting in which beta 1 can be consistently estimated by OLS, and that is the setting of randomized control trial. In a randomized control trial, x is randomly assigned according to a computer-generated random number that is independent of all the factors in U. When x is generated this way, x and u are independent and therefore orthogonal. And therefore, assumption A1 orthogonality condition is satisfied, and OLS of y on x will give us a consistent estimator for beta 1. Now I want to say one word about a convention. So in this course, when we say regress y on x, OLS regression of y on x, I implicitly included the constant in the regression. Okay, so constant is always implicitly included unless I say this is an OLS without a constant. Okay, as long as I don't specifically say constant is not included, it's assumed to be included. So, and another word is, so what do I mean by OLS of OLS regression of y on x? That simply means you are solving the minimization problem where you solve with respect to variables b0, b1, where you minimize the sum of squared residue and this is the OLS problem of regressing y on x. And the solution is called the OLS estimator from this OLS regression. Okay, equals argument, meaning that it's the b0, b1 that minimizes this sum of squared residue. And this beta 1 head consistently estimate beta 1 if the data comes from a randomized control trial where x is randomly assigned. Now, in almost all cases, a randomized control trial collects information beyond the treatment status x and the outcome y. For example, in this Oregon health insurance experiment, so this is another experiment, another RCT that is available for public use. In this OHI experiment, the government of Oregon, the state of Oregon, had some funding to expand Medicaid, which is a medical insurance for people who meet certain income eligibility standard. The state has some funding to expand Medicaid, but the funding is not enough to cover all eligible low-income uninsured adults. So what they decided to do is to randomize the treatment, randomize the Medicaid coverage. And the treatment was assigned by a lottery. So a lottery is according to a computer-generated number. So that is an RCT where the treatment variable is Medicaid, and the outcome, well, they include a bunch of outcomes. And besides the Medicaid variable and the outcome, the experiment also collected information on the demographic informations like age and gender, as well as the initial insurance coverage and healthcare experience. So this data set has this rich array of other covariates, other variables. Well, our estimator, the estimator we discussed last time, doesn't use this information. The question is, what can we do with these additional covariates? One option is to ignore them. Well, that's kind of fine because we already have a consistent estimator for the causal effect of Medicaid without using the covariates. But that seems kind of wasteful, so maybe we should use them. So option 2 is to use them. One simple way to use them is to include all of them in the OLS regression. Okay? Include all of them as explanatory variables in the OLS regression. Can we do that, and should we do that? Right, so in order to answer those questions, we need to answer these two questions. So first question is, will the additional covariates cause problem? Will we still get a consistent estimator for the causal effect after including all the additional covariates or some of the additional covariates in the OLS regression? If the answer is no, then clearly we shouldn't use these additional covariates because not using them, we already had a consistent estimator. But if the answer is yes, then we could use them, but should we use them? Whether we should use them or not relies on the answer to the second question. The second question is, will the new estimator be more accurate? The new estimator will be consistent if our answer to the first question is yes. But we already had a consistent estimator. Is the new estimator better in any way? And is it better in any way? We're going to study whether its asymptotic variance is smaller. So smaller variance is better for two consistent estimators. Okay, so today in this video, we'll try to answer these two questions in a semi-rigorous way using mathematics. Now, first, let's talk about consistency. Let me make the setting precise. Let W vector denote the vector of covariates we're thinking about including. Just to be concrete, let's consider the setting where Y is post-experiment earning, and X is a dummy variable indicating Medicaid coverage. So X is the treatment. And W includes age and gender, let's say, okay? And now we are thinking about including W in our OLS regression, meaning that we are thinking about running this longer OLS regression with both X and W as explanatory variables, okay? So to be more specific, regressing Y on X and W means that we solve the following minimization problem. We solve the problem that is B0, B1, BW, sum of the regression residual YI minus B0 minus B1XI minus BW, inner product wi squared. Okay, so running OLS regression of y on x and w means that we solve this minimization problem. And the solution to that is the OLS estimators for these coefficients. So in order not to confuse with the beta 0 hat and beta 1 hat before, let's call these gamma 0 hat, gamma 1 hat, and gamma w hat vector. Say gamma 0 hat, gamma 1 hat, and gamma w hat is the solution, is the argument, is the solution to this minimization problem, where gamma 1 hat correspond to the coefficient for x. So the question is whether gamma 1 hat consistently estimate our causal effect beta 1 hat, right? So notice that our target did not change. Our target is still the causal effect of Medicaid on post-experiment earning. So our causal model has not changed. Target is still beta 1, but our estimator has changed. Okay, estimator now comes from this different minimization problem. Is this new estimator still a consistent estimator for beta 1, for the causal effect of Medicaid? To answer that question, let's start with what we already know. Let's start with the question of what does OLS regression of y on x and w consistently estimate? Actually, we already know the answer to that question from the previous lecture. From the beginning of the previous lecture, we explained that the OLS estimator always consistently estimate the projection of the dependent variable on the explanatory variables. Okay, so the OLS estimator is always consistent for the projection model. It may or may not be consistent for the conditional mean model or the causal model, but it's always consistent for the projection model. The reason is the projection is always linear. So let's define the projection of y on x w be gamma 0 plus gamma 1x plus gamma w vector transpose w. Let this be the projection of y on x w. And let the projection error be y minus the projection. Then this is a projection model. Is a descriptive model, is the projection model. Not U, but epsilon is a projection model. And by the definition of epsilon, the epsilon satisfies the orthogonality condition. It's orthogonal to all the regressors in this equation. Okay, so the projection model always satisfies the orthogonality condition. Since for the discussion of this lecture and a few lectures later, we always assume A2 to A4 to hold. So IID assumption holds, no perfect multicollinearity hold, and finite kurtosis hold. So A2 and A4, we do not question them. And A1 also holds for this projection model by definition. Okay, A1 always holds for projection model. And therefore, OLS of y on x and w will consistently estimate these coefficients in the projection model. So what that means is the OLS coefficient on x in the multiple regression of y on x and w, that is the OLS estimators obtained from solving this minimization problem, consistently estimate gamma 1 in the projection equation. Okay. So we know gamma 1 hat converges in probability to gamma 1, and gamma 1 hat is the new estimator we're proposing for the causal effects. And our question was whether gamma 1 hat consistently estimate our causal effect, beta 1. So we know gamma 1 hat converges in probability to gamma 1. So our question turns into whether gamma 1 equals beta 1, right? So if beta 1 equals gamma 1, then gamma 1 hat also converges in probability to beta 1 because these two are equal. And gamma 1 hat is a consistent estimator for the causal effect in that case, right? So our question has turned into whether the causal effect equals the x coefficient in the projection, in this projection model of y on x and w. If it does, then our answer to the first question we started with would be yes, right? So including the additional covariates will still give us a consistent estimator for the causal effect. Now, let's see whether it does or not. Let's start with our target. So that is our causal model that we are interested in. And beta 1 is the coefficient in that causal model. We start with this thing. And then we try to find the projection of y on x and w using this equation. The projection of y on x and w equals the projection of beta 0 plus beta 1x plus u on x and w, because that is y. And the projection of the sum of two things equals the sum of the projection. Projection works like expectation in this sense. So the projection of the sum equals the sum of the projection And now the projection of this linear function of x on x and w should just be this linear function itself, right? So remember what projection means. Projection means that we are looking for a linear function of x and w to approximate the conditional mean of this given x and w. But the conditional mean of this given x and w is itself because it is a deterministic function of x, right? So what is the linear function of x and w that is closest to this function of x? Well, it's itself, right? Because itself is a linear function of x and w. There is not even any approximation error. So therefore, this projection is beta 0 plus beta 1x. But we cannot say the same for this projection. So we'll leave it here for now. So we'll leave it here for now. And then now we want to work on this using what we know about the RCT. So X is the treatment in the RCT, right, in the randomized control trial. So X was randomly assigned. Therefore, X is independent of U and W. So W are the individual characteristics that were observed before the treatment. And the treatment was assigned randomly, not according to the covariates. So therefore, X is independent of both U and W. When X is independent of both U and W, in fact, X kind of has no relationship whatsoever with U and W. So we can actually drop X out from this projection. Just to give you a bit more derivation on that, remember that independence means the probability density function follows this product rule. Independence means F, X, U, W. So that's the probability density function, joint probability density function of the three random variables. If X is independent of U and W, that means this probability density function can be factored into the marginal probability density function of X and the probability density function of U and W. Okay. And X is independent of U and W, so X is also independent of W. So another implication of that is Fxw can also be factored into the product of the marginal density of X and the marginal density of W. Then the conditional distribution of U given X and W by the conditional density formula, that should be the joint density of all three divided by the marginal density of X and W. But the joint density, as you can see, it equals this. So joint density on the numerator equals this product. And the joint density on the denominator equals this product. Right, so this ratio becomes the ratio of these two products. And we see this density of X crosses out because they are the same on the top and the bottom. So therefore, what we are left with is the ratio of this joint density of U and W divided by the marginal density of W, which is precisely the definition of the conditional density of U given W. So as you can see, in the conditional distribution of U given X and W, X drops out because X is independent of both U and W. And projection is a description, is an aspect of the conditional distribution of U given X and W. So if X can drop out of the entire conditional distribution, then X should also drop out of the projection. Okay, so therefore that implies X can drop out of this projection expression. So the ultimate reason is that X is randomly assigned. X is assigned according to a computer-generated random number independent of both U and W. So the lesson is the projection of U given X and W equals projection of U given W. Now, so remember the reason that we want to work on this projection of U given X and W is because it appears here in the formula for projection of Y on X and W. Now we know X can drop out of this projection. And this projection of U on W, by definition, projection is always linear on the conditioning variable. Therefore, the projection of U given W can always be written as this linear function of W for some scalar number of alpha 0 and some vector, non-random vector gamma W. Okay, so this can always be defined, so projection can always be written in this form for some value of alpha 0 and gamma W. And therefore, the projection of Y on X and W can be written as, so which is this from the previous 2 pages before. This can be written as beta 0 plus beta 1x plus projection of U given W, because X can drop out as we derived. And now we use this expression. Can write that as alpha 0 plus gamma W prime W. Now let's collect terms, collect all the constant terms. And there is only one X term and there is only one W term. So the projection of Y on X and W can be written as this linear function of X and W. And in particular, what's important is that the coefficient for X in this projection is beta 1, which is the causal effect that we are interested in. Okay, so the projection can be, the projection of Y and on X and W is this linear function of X and W. Importantly, the coefficient in that projection on X is the causal effect we are interested in. Okay. And remember, at the beginning, we already give projection of Y on XW this form. We let gamma 1 stand for the X coefficient. Now we derived a form for this, the same thing, from the causal model, from the expression of the causal equation. And we find the coefficient on X is beta 1. So therefore, this gamma 1 does equal to beta 1. Okay, so beta 1 is in fact the X coefficient in the projection. So that answers our first question. Okay. That is, including additional covariates does not cause inconsistency. We still have a consistent estimator after including those additional covariates. Okay. To reach this conclusion, notice that to reach this conclusion, we used these assumptions that X is randomly assigned. So X is independent of both U and W. Okay, so this is key for our derivation. If X is not independent of W, then this would not hold. Then adding the additional covariates W could affect consistency. But because we assume W is independent of X, it doesn't have this problem. So this usually is not a problem. So usually holds. So this usually holds when W only include pre-treatment variables that are the variables that were already determined before X was randomly assigned. Okay. So if on the other hand, W contains some post-treatment variables, then the treatment could be affecting the value of W, and there can be dependence between X and W, and including the W in the coefficient will not give us a consistent estimator for the overall causal effect of X. Okay, so we have found that if X was randomly assigned, comes from a randomized control trial, then either including additional pretreatment variables as covariates or not including them, either way, we'll get a consistent estimator for the causal effect beta 1. But then you might wonder, then how do we choose between the two versions? What's the point of including the additional covariates if all it does is to produce a second consistent estimator? So the answer to that relies on the accuracy of the estimator. Does including additional covariates under RCT improve accuracy of the estimator? The answer is actually yes. Including covariates under RCT may help in estimation accuracy. What that means specifically is the following. The estimator for beta 1, when you run OLS with the covariates W's, may have a smaller asymptotic variance than from OLS without the covariates W's. So including the covariates may give us an estimator that has a smaller asymptotic variance. Okay, so in other words, so using the notation that we used before, the asymptotic variance of beta 1 hat, which is the OLS estimator for beta 1, not using the covariates W, that is weakly greater than asymptotic variance of gamma 1 hat, typically. Gamma 1 hat is the estimator for beta 1 when you do use the covariates W. Okay, so typically. And why is this the case? We're going to show that in the rest of this video. First, I want to give you an intuition for why including more covariates can improve accuracy. So when we estimate this equation, this causal equation, okay, in this causal equation, X is a treatment. X is part of the factors, is one factor that contributes to Y, and U summarizes all other factors. Because of U, because of this unobservable U, we are not able to find the exact relationship between the treatment and Y, and that is why our OLS estimator has a positive variance. So U is unobservable. That's the noise that hurts estimation accuracy, that causes inaccuracy in our estimator. And adding W to the equation is like picking out some of the factors in U and leaving less factors, fewer factors in the error term. Okay, So adding W to the equation is reducing what's left in the error term. And therefore, it's reducing the noise. So for that reason, intuitively, it should improve accuracy in the estimation. Consider the very extreme case where U is W, U is observable, so therefore it is W. Then clearly including it will completely eliminate noise. We will have an exact estimate for beta 1. We'll be able to know beta 1 exactly if we do observe U precisely. Of course, we never do, but suppose that we do. Then we completely eliminate noise and our estimator will be exactly correct. And in practice, U is never observable, but we may be able to observe part of U through W. Okay, and that is the intuition behind why W is helpful. And now let's be somewhat more rigorous and give some more details on that intuition and see why mathematically that makes sense. Let's start with the simple linear regression, simple linear model. Okay, that's our simple linear causal model. Okay, and we are interested in estimating beta 1, the causal effect of X. So still beta hat denote the OLS estimator from the short regression, the OLS regression of Y on only X. The asymptotic variance of root n times beta hat is given by this formula, which we derived in 2 lectures ago. I think one of you asked me in lecture, so why is this asymptotic variance of root n beta hat? Why is it not? So what we did derive is this, is beta hat vector minus beta vector converges in distribution to normal V, where this is V. So what this means is normal 0V is the approximate distribution of this random vector, and V is the approximate variance or asymptotic variance of this random vector. Then why is the asymptotic variance of this is the same as asymptotic variance of this without the centering? Well, that's simply because this is a non-random constant. Right? This is the true value of the parameter. It's non-random. So adding non-random or subtracting non-random vectors from a random vector does not affect the variance covariance matrix. So that's why the asymptotic variance of this is the same as the asymptotic variance of this. So that's why I write asymptotic variance of root n beta hat vector. To write that to be equal to V. So I set that to be equal to V. Okay, so that's a digress. Now we use this formula to derive the asymptotic variance of the second element, because we do not care about the estimator for the intercept in the causal model now. We only care about this treatment effect now. Okay, so let's use that formula to derive the asymptotic variance of the second element, beta 1 hat. It turns out the beta 1 hat has asymptotic variance that's given by this. How do you get that? You can do that by using matrix manipulations. So V, we can start with the formula for V. V is Ex x prime inverse times E u square x inverse x prime and times x prime inverse. So what is this matrix? This matrix E x transpose is E 1x because we only have one x variable and one constant variable. And that is E of 1x squared. So therefore, V equals expectation of this matrix inverse. So that is 1 EX squared inverse. Similarly, you can write this also into a 2 by 2 matrix, write out that thing. So that should be u squared times x, u squared times x, and u squared x squared. Right, so that should just be u squared u squared x u squared x u squared x squared. So now we want to do this multiplication to find that 2 by 2 matrix, and in particular we want to find that the second diagonal element, because the second diagonal element corresponds to the asymptotic variance of the second element for that random vector beta hat. Okay. So what's the inverse of this 2 by 2 matrix? So using the inverse formula for 2 by 2 matrices, so that should be EX squared minus EX squared. So that's diagonal product minus the off diagonal product, 1 over that, times EX squared 1 minus EX minus EX. So that's the formula for taking the inverse of a 2 by 2 matrix. So I'm gonna copy everything here. And then that inverse, we can do the same thing. Okay, so now that is V. Now we simply need to just multiply everything out. Notice that this is the variance of x, and that's also the variance of x. So you got 1 over variance of x squared already. And now do this multiplication. We find that should be EX squared minus EX times this. So that is EX squared EU squared minus EX EU squared X. And the second element is this times that. So that is EX squared EU squared X minus EX EU squared X squared. And then the second row, first column is this, is u squared x minus ex eu squared. And the second row, second column is eu squared x squared minus ex eu squared x times this thing. Times this. So let's keep working on this. But we really don't care about the other elements of this matrix. We only care about the second row, second column, because that is the asymptotic variance for the second element of beta hat vector. And so let's not even calculate the other elements. So first row, first column, we don't care about. First row, second column, we don't care about. Second row, second column, we don't care about. Let's only calculate the second row and second column and see what that is. And that should be this times 1 plus this times minus ex. So that's eu squared x squared minus ex eu squared x minus ex times eu squared x plus ex squared eu squared. So that should be eu squared x squared. So now we collect all the u squares, put everything into one big E. So you see these two terms are the same. So we can erase one of the terms and put a 2 on the other and put everything in a big expectation. Then the first term is u squared x squared minus 2 ex, which is a constant that can enter this expectation. And that expectation is the one that we take out. So that's ex times x plus ex squared. Sorry, ex squared u squared. Notice that this u squared can be factored out. Once the u squared is factored out, we're left with x squared minus 2exx plus ex squared. So that's precisely x minus ex squared. So that is this numerator. So we got this numerator. This is the numerator for that second asymptotic variance of the second element of beta hat. And that's the denominator. So we have finished our derivation of this form. So asymptotic variance of root n beta 1 hat, that's our estimator for the causal effect, is of this form. So if you look at this, this actually can be written using the law of iterated expectations. This can be written as expected value of conditional expectation of what's inside given x, and x minus ex squared can be taken out of that conditional expectation because it is a non-random function of x. So therefore inside we have the conditional expectation of u squared given x. Next, in order to make it simpler, make it cleaner, we're going to assume for now Homo Scadasticity, which means expected value of u squared given x equals a constant. Let's assume this Homo Scadasticity for now, just for this part of the lecture. Okay, assume that is the case. Then that is sigma squared, so it's a constant. And the sigma squared can come out of the expectation, and what's left is expectation of x minus ex squared. And that expectation is the variance of x. So on top you have a variance of x, on bottom you have a square of variance of x. One of the variance of x cancels out, so you get sigma squared divided by just one variance of x. So the asymptotic variance of root n times the causal effect estimator in the OLS regression without the additional covariates can be written as this, if homoscedasticity holds. Okay. This is a rather intuitive formula because it's a ratio of the variance for the error and the variance for the regressor. So high variance of the regressor helps with estimation accuracy. So high variance of x reduces asymptotic variance for the estimator. So you want the regressor to have high variation. And you do not want the error term to have high variation. So high variation of the error term hurts estimation accuracy. So this is intuitive because the variation of x, the variation of treatment, is our information about the treatment effect, while the variance of the other uncontrolled factors is the noise that affects our ability to estimate our causal effect accurately. Okay. So high variation of x reduces the asymptotic variance, high variation of u hurts estimation accuracy. So that's what this final formula tells us. Now we want to compare asymptotic variance of this beta 1 hat, this estimator of beta 1 from the simple regression to the asymptotic variance of the beta 1 estimator with the additional covariates. Okay. Now suppose we run the OLS regression including the additional covariates W. Let the new estimator be denoted beta 1m, which we already had a term that is gamma 1 hat. Gamma 1 hat was the notation we had a few slides before, but now let's just make it more intuitive and call that estimator beta 1m. So it just means that we are still estimating beta 1, just make it clear that we are still estimating beta 1. And this comes from the multiple regression, including the additional covariates. So this M stands for M multiple regression, okay? So this new estimator has an asymptotic variance that is of this formula, of this form. So I'm gonna state this without a proof because proving this, it's kind of tedious. It's not difficult, but it's very tedious. So I state that asymptotic variance of this estimator coming from this long regression is of this form, which as you can see, it's very familiar to you, right? So it's almost the same as this. It's nearly the same as the asymptotic variance of root n beta 1 hat, where the estimator come from the simple regression. From the estimator from the multiple regression is almost the same as that, except now the u and the x are different. And the u and the x are, instead of the original error term u, it is the original error term after projecting U on W is the projection residual after projecting on the additional covariates. So this U tilde, you can imagine it is U with a linear function of W removed from it. Okay, so U tilde is U with W removed, roughly speaking. And X tilde is X with W removed. So we state without proof that this holds for the multiple regression estimator. And similarly, let's also make the simplifying assumption, the Homo scadasticity assumption. Let's say EU tilde squared given X tilde is a constant. It's not a function of X tilde. Let's make this Homo scadasticity assumption as well. Then following the same logic, we can derive that this asymptotic variance equals sigma tilde squared divided by variance of X tilde. So it's almost the same as the simple regression estimator. They are of the same form, except that sigma squared is the variance of the original error term in the causal equation, while sigma tilde squared is the variance of the original error term with W removed. And the bottom is the same story. X is the original causal variable, treatment variable, and X tilde is the treatment variable with W removed linearly. So these representations is going to be the basis that we compare these two. See which one is bigger. Before comparing them, I want to stress that these representations require the simplifying Homo scadasticity assumptions, but it does not really require RCT. So the derivation did not use the RCT assumption except EU EXU equals 0. So the formula actually applied to other settings other than the RCT setting as long as EU equals EXU equals 0. And even though we assume Homo scadasticity when we derive these two, the intuition conveyed in our comparison that we're going to present right now applies more generally, even when Homo scadasticity doesn't hold. But for simplicity, for presentation purposes, we just assume Homo scadasticity. So we have this simple result. Now let's compare. Let's go back to the RCT setting. Okay, the comparison here now only applied to the RCT setting. Now let's go back to the RCT setting and compare these two ratios. In the RCT setting, X is randomly assigned. Therefore, it is independent of the additional covariates W. So X is independent of the covariates W. What that means is this. The independence means this. Means that independence means mean independence. Well, independence doesn't mean mean independence. Independence implies mean independence. Okay, independence is stronger than mean independence. So in X being independent of W implies that the conditional mean of X given W does not depend on W. That means a conditional mean of X given W is a constant. Conditional mean is a constant. Constant is a trivial linear function of W, so therefore the conditional mean is trivially linear in W with a 0 coefficient on the W. And therefore the projection equals that also, equals that trivial linear function. So the projection of X on W also equals this constant. projection is a constant. It doesn't depend on W, it's a number. So x tilde is x minus a non-random number. Subtracting or adding non-random number to a random variable doesn't affect the variance. So therefore in RCT, the bottom of these two estimators are the same. Variance of x tilde equals variance of x because their difference is only a constant. So the bottom is the same. Now let's compare the top, the numerator. To compare the numerator, we notice that u tilde is the difference between u and the projection of u on W. So therefore u equals the projection of u on W plus u tilde. So u tilde is actually the projection error of u on W. So if you write the projection as, say, delta 0 plus delta 1 prime W, then u is the delta 0 plus delta 1 W plus u tilde. So in fact, this is a projection model for u. Okay. U is now the dependent variable in this projection model. And u tilde is the projection error. Right? So if you call this y and call this u, then this is more familiar to you, right? So this notation is more familiar to you. But now we're just using a different notation for the dependent variable and for the projection error. The essence stays the same. This is the dependent variable, and this is the projection error of the dependent variable on W. So what do we know about projection error? Projection error is orthogonal to the variables u is projected upon. So therefore, u tilde should be orthogonal to W. And u tilde should have mean zero by the definition of projection. And because this is the case, projection is the linear function of W, therefore u tilde should also be orthogonal to the linear function of W, right? So that implies expectation of delta 0 plus delta 1 tilde W times u tilde should be 0. And that is the covariance because the expectation of u equals 0, right? So because that is the covariance, covariance plus expectation of one variable times expectation of the other variable, well, the other variable equals 0. So therefore that's 0. So that expectation equals the covariance. So that implies this covariance of the projection and u tilde is 0. So now u is the sum of these two random variables, and the covariance between the two random variables is 0. Therefore, the variance of the sum equals the sum of the variance. In general, variance of the sum is not equal to the sum of the variance. In general, the variance of the sum equals the sum of the variance plus 2 times the covariance. But now the covariance equals 0. So therefore, the variance of the sum equals the sum of the variance. So we have obtained a relationship between the variance of u and the variance of u tilde. So sigma squared, or in other words, a relationship between sigma squared and sigma tilde squared. So the relationship between sigma squared and sigma tilde squared is this. Sigma squared is variance of this projection plus sigma tilde squared. Because the variance of any random variable is non-negative, therefore sigma squared should be weakly bigger than sigma tilde squared. And it's only equal when the projection of u on w is a constant, have a zero variance. So it's only equal if projection of u on w is a constant. But in general, sigma squared is bigger than sigma tilde squared. So what we have derived is, in the formula of these two asymptotic variances, the denominators are equal and the numerators have this relationship. That means asymptotic variance of the estimator from the regression not using the covariates is weakly bigger than the one with the covariates. So including the covariates weakly reduces the asymptotic variance of our causal effect estimator. So what we are saying is adding covariates is helpful in randomized control trial. I want to stress in randomized control trial because this is not generally true, only in randomized control trial. Adding covariates W that are independent of the treatment does not cause inconsistency, and it does reduce asymptotic variance unless W is completely irrelevant, meaning that the projection of U on W is a constant. In which case it doesn't help or hurt. Okay, so adding covariates is almost always helpful in randomized control trial. Notice that all the derivations were not reliant on a linear relationship between U and W. We do not need U to depend on W linearly, or in other words, we do not need E of U given W to be linear. We do not need a conditional mean of U given W to be linear in order for adding W to be helpful. In fact, functional form for this does not matter for our conclusion. What that also means, you can add nonlinear terms of W as well as additional regressors. Maybe that could reduce asymptotic variance even further. So, but when you do that, just remember not to include too many of them for your sample size. If your sample size is 100, maybe you shouldn't include 20 W's, because the problem with too many covariates in a regression in a small sample is that the asymptotic variance no longer describe the actual variance of the estimator. The actual variance could be bigger, and there might be even finite sample bias in the estimator. Okay, so just don't go overboard when you are considering adding all kinds of nonlinear terms of W in the regression when you want to estimate beta 1 consistently and accurately.